Have you ever wondered how friendship can form complex networks? Imagine you are at a party and you spot a small group of friends laughing and chatting. But what if I told you that those friendships can be analyzed mathematically? Today we are diving into the fascinating world of cliques in graph theory. Stick around as we unravel how these social connections can be represented through algorithms and why they matter more than you think. Alright, let's dive into the problem which revolves around finding the largest clique size that can exist within a given graph structure without surpassing a specific number of edges. First, we start with our input. We read in an integer t which tells us how many test cases we are dealing with. This is key because we want our solution to be versatile, able to handle multiple scenarios in one go. Next, for each test case, we gather two important pieces of information, n and m. Here, n represents the number of vertices in our graph and m is the maximum number of edges we can form without forming a clique of size greater than what we are trying to find. So why is knowing these two values important? It sets the stage for the entire logic and determine how we'll approach the problem. Now we introduce our search range. We set low to 1 and high to n. This range represents the potential size of the clique we are looking for. We want to determine the largest clique size we can have while keeping the edges count within the limits imposed by m. So we start with an initial assumption that the largest clique could be as big as n itself. Here comes the core of the algorithm, a binary search. This is where this method is efficient because it allows us to eliminate half of the space search with each iteration. We calculate the midpoint m of our current range. Now the real question is, can we have a clique of size mid without exceeding m edges? To answer that, we call the max edges without clique function, which uses Turán's theorem, a powerful combination graph theory. This theorem helps us calculate the maximum edges that can exist in a graph without forming a clique of R. The formula here incorporates N and R, giving us a way to quantify the edge limits based on the size of the cliques we are testing. If the maximum edges that can exist without forming a clique of size mid is less than M, we can potentially increase our clique size. So to adjust our search range, we by moving low up to mid plus 1. Conversely, we can't form a clique of size mid without exiting M, and we have to scale back. So we have to set high to mid minus 1 and keep track of our last valid mid in N. This back and forth continues until we have exhausted our search space, honing in on the largest possible cliques that fit criteria. Finally, once we are settled in our result and that test case and for the test case, we print it out. This structured approach allows us to efficiently navigate the problem space and find our solution without getting lost in the complexity of the graph itself. So to summarize, we are leveraging binary search to efficiently pinpoint the maximum cliques size using a mathematical theorem to guide our edge calculations. It's a beautiful blend of theory and practice, and it shows how powerful strategic thinking can be used in coding. Alright folks, let's quickly recap what we have covered. We have taken a fascinating problem from HackerRank regarding finding the size of the largest clique in a graph, and boy did we dive deeper into more impressive coding techniques. Yes, we have implemented a binary search algorithm to efficiently determine the largest clique size, leveraging Turán's theorem to calculate the maximum number of edges without forming a clique. This approach not only optimizes our search but also handles larger input with ease. The main key takeaway here is the powerful combination of binary search and mathematical theorem to solve graph-related problems efficiently. By understanding how to manipulate ranges and apply theoretical concepts, you can tackle complex challenges like this one with confidence. If you have found this solution enlightening, don't forget to give it a thumbs up and subscribe for more coding challenges. Make sure to check out the source code link in the description below, and stay tuned. In our next videos, we'll explore more into advanced graph theorems and even to real world applications of these concepts. You don't want to miss it. Until next time, keep coding and keep challenging yourself.